Welcome to the deep dive. Today, we're diving into the world of MLOps, and we're going to be guided by some fascinating research from CSIRO Data 61. Now, you're no stranger to mathematics, machine learning, and data science, so we're skipping the MLOps 101, and we're heading straight for the advanced insights. This research is essentially it's a survey of surveys about MLOps, compiling insights from various publications and real-world best practices. So think of it as like a cheat sheet to the current state of MLOps, distilled by experts for experts.
It really is a comprehensive view of the entire ML process, and not just building models, but the whole 9 yards.
That's right. And they've laid it all out in an 8-step MLOps process. It starts with what they call model requirement. That moves through data collection, data preparation, feature engineering, model training, model evaluation, model deployment, and finally model monitoring. But before we jump in, let me ask you this. Did you know that 80% of the effort in a successful machine learning project goes into everything but model training?
That statistic really highlights why robust MLOps are so crucial. We need to optimize the entire life cycle, not just the model building. And this first step, this model requirement phase, is where so many projects stumble. It's about identifying the right problem to solve with ML, which is more nuanced than in traditional software development.
It definitely feels like a different beast. I've seen so many projects where the problem definition was vague, and they ended up like trying to force fit a model into a situation where it just didn't belong.
Yeah, I've seen it too. The paper breaks down model requirements into 4 key dimensions. First, you have business value. This seems obvious, but it's surprising how often projects lack a clearly defined ROI. You need to understand why you're building this model and what tangible benefit it will bring.
Makes sense. If you can't articulate the why, you're probably heading down the wrong path. But what about the quality of model? Is that just about accuracy?
It goes beyond that. Accuracy is important, of course, but you also need to consider robustness, which is the model's ability to handle noisy or unexpected data. Then there's generalization ability. How well does it perform on unseen data? And let's not forget simplicity. A simpler model is often easier to understand and maintain. Finally, there's consistency, ensuring that the model's internal logic is sound and doesn't contradict itself.
So it's like building a house. Accuracy is the foundation, but you need strong walls, robustness, a roof that doesn't leak, generalization, and a design that makes sense, simplicity and consistency.
Exactly. And then we get to the human element, which adds another layer of complexity. The paper emphasizes that human values like privacy, fairness, security, and accountability need to be baked into the MLOps process from the very beginning.
And that brings us to ethics, which takes these human values a step further. We're talking about the broader societal impact of the model, going beyond just legal compliance.
Right. We've seen countless examples of models perpetuating biases or being used in ways that raise ethical concerns. Facial recognition for surveillance, or algorithms that discriminate in hiring are prime examples. So while we can't delve into every nuance here, it's crucial to consider these ethical implications early on.
It's a lot to consider, but without solid foundations in these model requirements, everything else built on top is shaky. Now, let's talk about the fuel that powers any machine learning project: data. I was struck by that statistic we mentioned earlier. 80% of a project's time going into data preparation. That's a huge chunk.
It is. And this paper really dives into the nitty-gritty of data collection and preparation. It all starts with identifying the right data sources. Do you have existing data sets you can leverage? Can you augment them with external data? Or do you need to generate synthetic data? The paper advocates for a centralized data repository, like a data lake, to manage all of this.
A data lake. Sounds like a pretty massive undertaking.
It can be, but think of it as a one-stop shop for all your data needs. It's a scalable and flexible way to store and manage both structured and unstructured data, which is crucial in complex ML projects. But even with a data lake, you can't just dump everything in and expect magic to happen.
You need to wrangle that data into a usable format. That's where data ETL comes in, right? Extraction, transform, load.
Precisely. It's about pulling data from various sources, cleaning and transforming it into a consistent format, and then loading it into your data lake or other centralized location.
The paper mentions data cleaning and data merging as crucial steps within data preparation. It sounds pretty straightforward. but I bet there are hidden complexities.
Oh, yeah. Especially when you're dealing with real-world data, which is often messy and inconsistent. You might have missing values, duplicates, or inconsistencies in data types. Data merging can also be tricky, especially when you're dealing with data from multiple sources with different formats and schemas. The paper goes into detail on various techniques for addressing these challenges.
So we've got our data lake. We've cleaned and merged the data, and now we need to make sense of it all. That's where exploratory data analysis, or EDA, comes into play, right?
Absolutely. EDA is like putting on your detective hat and getting to know your data intimately. You visualize it, identify patterns and trends, spot outliers and anomalies. It's about gaining insights that can inform your feature engineering and modeling decisions.
It's about asking the data the right questions before you start trying to answer them with models.
Exactly. And sometimes EDA reveals surprising insights that you might have missed otherwise. It can even lead you to rethink your initial problem definition or identify new opportunities for model development.
Okay, we've got clean, merged, and explored data. What happens next?
That brings us to feature engineering, which is where we transform that raw data into powerful predictors for our models. Think of it as crafting the ingredients that will make our ML recipe truly sing. Feature engineering is a crucial but often overlooked aspect of the ML lifecycle. It can make or break your model's performance. This paper dives into 4 key aspects: feature selection, feature construction, feature scaling, and data labeling.
Let's start with feature selection. Isn't that just about picking the right variables?
It's a bit more nuanced than that. You're right. It is about choosing the most relevant features from your dataset, the ones that have the greatest predictive power. But the challenge lies in choosing the right method for your specific data and model.
The paper mentions filter, wrapper, and embedded methods. Can you break those down for me?
Sure, filter methods are relatively simple. They rank features based on statistical measures, like correlation or information gain. Wrapper methods, on the other hand, use the model itself to evaluate different feature subsets. This can be more computationally expensive, but often leads to better results. Finally, embedded methods incorporate feature selection into the model training process itself. Think of it as the model learning which features are most important as it goes.
So the choice of method depends on factors like the size of your data set, the complexity of your model, and the computational resources you have available.
Exactly. And it's not always a clear-cut decision. Sometimes you need to experiment with different methods to find the best approach for your particular problem.
Now, what about feature construction? That sounds like we're creating new features from our existing data.
That's right. This is where domain expertise and creativity really shine. You might combine existing features, transform them mathematically, or generate new features based on your understanding of the problem. The paper mentions techniques like decision trees, genetic programming, and annotation-based approaches, all of which can uncover hidden patterns in your data.
It's like adding secret ingredients to your recipe to enhance the flavor.
I like that analogy. And just like in cooking, feature construction requires a combination of art and science. You need to understand the data, the problem, and the available techniques to create features that truly boost your model's performance.
We've selected and constructed our features. What's next?
Before we move on to model training, we need to ensure that our features are on a similar scale. This is called feature scaling.
Why is that necessary?
Many machine learning algorithms are sensitive to the scale of the features. If one feature has a much larger range than another, it can dominate the learning process and lead to suboptimal results. Feature scaling levels the playing field, so to speak.
The paper mentions normalization as a common technique.
Normalization is a good example. It rescales features to a standard range, typically between 0 and 1. This ensures that all features contribute equally to the model's learning process.
And finally, we have data labeling. This is about assigning meaningful tags or categories to our data points, right?
Exactly. Data labeling is essential for supervised learning, where the model learns from labeled examples. The paper delves into different labeling approaches, from using existing labels to crowdsourcing and even weak labeling, where labels are less precise, but can be obtained more easily.
It sounds like there's a trade-off between accuracy and efficiency when it comes to data labeling.
There is. High-quality labels are crucial for model performance, but they can be time-consuming and expensive to obtain. Sometimes weak labeling is a pragmatic approach, especially when dealing with large data sets.
Okay, we've talked about data requirements, data prep, and feature engineering. That brings us to the heart of machine learning, the model itself.
Right, the algorithms. This is where we choose the right tool for the job, based on the data, the problem, and the desired outcome.
The paper assumes our listener is already familiar with the 4 main types of models. supervised, unsupervised, semi-supervised, and reinforcement learning. But I'm curious from your experience, which type do you find yourself using most often, and why?
It really depends on the task at hand. But I'd say supervised learning is probably the most common, at least in my work. That's where you have labeled data, and you're trying to train a model to predict a specific outcome. Think of it as teaching the model by example.
Makes sense. Now, the paper talks about model selection.
Right.
This is where we choose the best model for the problem, right? But with so many algorithms out there, how do we even begin to narrow it down?
It's a combination of experience, intuition, and a bit of trial and error. You consider factors like the type of data, the complexity of the problem, and the desired performance metrics. But you also need to experiment. You might try different algorithms, tweak hyperparameters, and evaluate their performance on a holdout data set.
The paper mentions resampling methods like cross-validation and bootstrapping. Can you explain how those help with model selection?
Resampling methods are like running multiple mini-experiments within your data. Cross-validation, for example, splits your data into multiple folds. You train the model on some of the folds and test it on the remaining fold. You repeat this process multiple times, each time using a different fold for testing. This gives you a more robust estimate of the model's performance than just using a single train test split.
So it's like getting multiple opinions before making a decision.
Exactly. And bootstrapping is another resampling method. It involves creating multiple data sets. By randomly sampling from your original data with replacement, you train the model on each of these bootstrap data sets and then average the results. This helps you assess the model's stability and variability.
Okay, we've trained our model, we've selected the best one using these resampling methods. Now it's time for the moment of truth, model evaluation.
This is where we assess how well our model performs on unseen data. But as the paper points out, it's about more than just accuracy. We need to consider a range of metrics to get a complete picture of the model's strengths and weaknesses.
Metrics like precision, recall, F1 score, confusion matrices, ROC curves, the list goes on. It can be overwhelming to know which metrics to focus on.
It is, and it really depends on the specific problem and the intended use of the model. If you're building a spam filter, for example, you might prioritize precision, which measures how many of the emails you classify as spam are actually spam. But if you're building a fraud detection model, you might prioritize recall, which measures how many of the actual fraudulent transactions you correctly identify.
So the choice of evaluation metrics is tied back to those model requirements we talked about earlier.
Absolutely. You need to align your metrics with the goals and values that you defined at the outset.
All right, so we've built our model, trained it on high-quality data, and rigorously evaluated its performance. What's next? Time to release it into the wild.
Well, not so fast. That brings us to model deployment, which is where we take our model from the lab and make it work in the real world.
Deployment can be as challenging as model building itself.
Oh, absolutely.
It's about choosing the right deployment environment and infrastructure, ensuring scalability and reliability, and integrating the model seamlessly into existing systems.
It really is.
The paper mentions different deployment methods, including web applications, batch predictions, and embedded models. Is there a one-size-fits-all approach here?
Not really. The choice of deployment method depends on a number of factors, like the model's complexity, the required latency, the volume of data, and the available infrastructure. Web applications are great for real-time predictions. Batch predictions are more suitable for offline processing of large data sets. And embedded models are ideal for devices with limited computational resources.
So we've deployed our model. It's out there making predictions. Are we done?
Not quite. The real world is a dynamic environment. Data can change over time, new patterns can emerge, and even the underlying problem that you're trying to solve can evolve. This is where model monitoring comes in.
It's about making sure the model is still doing its job effectively, even as the world around it changes.
Exactly. The paper discusses various monitoring techniques, such as adaptive windowing and statistical process control, to detect changes in data distribution or model performance. It also emphasizes the importance of system logging to track model behavior and identify potential issues.
This all ties back to that 80% statistic we talked about earlier. It's not just about building and deploying the model. It's about the ongoing maintenance and monitoring that keep it running smoothly.
Exactly. And it's not just about technical monitoring. We also need to consider the ethical implications of our models over time. Are they still aligned with the values we defined at the outset? Are they having any unintended consequences?
It sounds like a constant process of evaluation and adjustment.
It is. MLOps is an iterative cycle, not a linear process. You build, deploy, monitor, and learn. Then you use those learnings to improve your model, your data, and your entire ML pipeline.
So as an expert in this field, what are your biggest takeaways from this research? What stands out as the most valuable insights for our listeners?
I think the paper does a fantastic job of emphasizing the holistic nature of MLOps. It's not just about building accurate models. It's about building robust, ethical, and sustainable ML systems that deliver real-world value. It's about data quality, feature engineering, model deployment, monitoring, and continuous improvement.
It's about the entire life cycle, from conception to retirement.
Exactly. And I think this research serves as a valuable reminder, even for seasoned ML practitioners, that MLOps is a constantly evolving field. We need to stay informed about the latest best practices, tools, and techniques to ensure that our work is not only technically sound, but also ethically responsible and aligned with human values.
It's a lot to consider. But that's what makes this field so fascinating. So for our listeners, those who are already deep in the trenches of machine learning, what's the one thing you would like them to take away from this deep dive?
I'd say this: embrace the complexity. Don't shy away from the challenges of MLOps. It's in those challenges that we find the greatest opportunities for innovation and impact.
It's about pushing the boundaries of what's possible, while always keeping in mind the ethical implications of our work.
Absolutely.
This deep dive has given us a lot to think about. As the world of machine learning continues to evolve, so too will the field of MLOps. What do you think the future holds for MLOps? What are the biggest challenges and opportunities on the horizon? We'd love to hear your thoughts. Be sure to check out the show notes for links to the CSIR Data 61 research paper and other resources. Until next time, keep diving deep.